Let's take a look at another example of a language that accepts bit sequences containing the pattern 101. We're going to look at this from two different perspectives. One is using a DFA, a deterministic finite automata, and the second is going to use an NFA, a non-deterministic finite automata. So with our deterministic finite automata, we will have a start state, as we always have. And so I will label this as start and identify this as an initial state. Then what I want to do is I want to start reading the bit sequence, and as I encounter the pattern 101, if I ever move through those 3 bits in sequence, then I would end up in a final state, and then anything after that would be just extra bits, and that's fine. If I start to see the pattern but then it falls apart, then I'm going to have to go back. So from the start state, if I see a 0, then that's not making any progress towards finding our pattern, so I'm just going to stay in the start state in that situation. However, if I see a 1, then that's making some progress. So we'll have a new state that I will label as having seen a 1, and I get there from the start state on a 1 transition. Now, in this state, if I see a 0 next, then I'm actually making better progress towards my pattern of 101. And so I'm going to move into a new state in this case. And I will label this as my 10 state, meaning that at this point I've seen the pattern 10 so far. And I get there after having seen a 1, I get there if I see a 0 next. Now, the bad news is that if I see a 1 in this state, that doesn't actually get me any closer to the final state. But the good news is that it's going to get me a little bit closer to the, it doesn't get me any further away either. So I will just stay in this state saying I've just read a 1 and I'm hoping to see a 0 next. Now, I'm going to deal with this state here where I've already seen a 1 and I've already seen a 0 back to back. At this point, if I see a 0, that is not helpful at all because I'm going to end up not having the pattern of 101, and in fact I have to start from the beginning. So a 0 means I'm going to end up going back to the start state. And I have to hope to see a 1 as a bit in the future to start off the pattern of 101. However, from here, if I do happen to see a 1, then I now have seen the pattern 101 in sequence. So I can now introduce a new final state, a new state which will be a final state. So I'm going to mark this as having seen my pattern 101. I'm going to designate this as a final state, and I get there from this state having seen 10 in sequence. Now I get there on seeing another 1. Now I have dealt with all of the possible inputs for all the states except for the final state. So from the start state on a 1 I go here, on a 0 I stay, from this state on a 1 I stay, a 0 I move on to this state. From this state, if I see a 0 I have to go back to the start, but if I see a 1 I move into the final state. The last thing to do is deal with the case where if I have more bits after I see the pattern 101, I have to read those bits. But I've seen the pattern, and so that's just going to keep me in the final state. So on a 0 or on a 1, I stay in the final state. And this is a DFA that will handle the case of recognizing strings that contain the pattern 101. And this isn't too bad. But there's a little more natural way to think about this problem. Basically, if I want to recognize the string that contains the pattern 101, I can have as many 1s and 0s as I want before that pattern, and then I see that pattern, and then I have as many 1s and 0s as I'd like after that pattern. That's the way I would think about it abstractly. The DFA doesn't allow for that kind of flexibility however. But an NFA, or a non-deterministic finite automata, would allow for that kind of flexibility. So we'll take a look at another solution to this, which uses an NFA rather than a DFA. So again, I'm going to have my start state as I did before, and I will designate it as a start state and identify it as a start state. And then what I do is I basically create states that are showing me the pattern. So I have, I move to the next state if I read a 1, and I will designate this as my state 1. I move to, if I read a 0, I would move on to the next state, and I designate this as my 1, 0 state. And then if I read 1 following that, I end up in a final state. And that's sort of my pattern has been taken care of. I'm going to designate this as my 1, 0, 1 state and create this as a final state. And just line things up a little bit better here. And then I essentially just deal with the idea of having as many 1s and 0s as I like before this pattern, and as many 1s and 0s as I like after this pattern, the way that I've just described it. And that's to say that if I'm in the start state, I can see as many 1s and 0s as I like. So I can read a 0 here, or I could read a 1 here, and I can read as many 1s and 0s as I like. But then if I see the pattern 1, 0, 1, then I'm going to run into, I'm going to make my progress towards the final state. And then I can see as many 1s as 0s as I like in the final state. So again, I'll read a 0 or I'll read a 1, and that's fine. And this is sort of more naturally the way I would think about the problem. I can see a bunch of 1s and 0s, but then as soon as I see the pattern 1, 0, 1, I reach the final state. And then I can see as many 1s and 0s as I like from here. The problem is that this is no longer a deterministic finite automata. And the reason for that is when I'm in the start state and I recognize that I have a 1, I don't know exactly where to go at this point. I'm stuck because I have the option of either moving into the 1 state or I can stay in the start state. So the 1 could be the beginning of a 1, 0, 1 pattern, or it could be something that isn't part of that pattern. I could see a series of 6 1s, and that doesn't get me any closer to the final state. So this makes it non-deterministic. So a non-deterministic finite automata says that I have states in my finite state machine where I would have a choice on the same input of going to more than one possible new state. There are a couple of other features of an NFA, and that includes the idea of something called a lambda transition, which means I can just jump to one state from another state without actually having read any input. That's a feature of an NFA that is not a feature of a DFA. How do we evaluate input on an NFA? Well, we can sort of think about the idea of having clones, where we have, every time we have an input that has multiple choices, we clone ourselves and we move to both choices, or all 3 choices, or however many choices there are, to those states. And we just continue progressing through the string until either we don't have anywhere to go, one of our clones doesn't have anywhere to go, and that clone dies, or we reach the end of the string. Basically, at that point, we know that we have accepted a string if at least one of our clones ends up in the final state. There are obvious design advantages to an NFA over a DFA. It gives us much more flexibility than a DFA in terms of design, and it oftentimes makes the finite state machine much simpler than we would see in a DFA. The reason to think about using a DFA rather than an NFA is that the evaluation part of the string, recognizing whether the string is accepted or not accepted, is much simpler in the context of an of a DFA than in an NFA. We don't have this idea of these clones going along, and there's some kind of parallel processing happening. So NFAs oftentimes are easier to design. DFAs are almost always easier to evaluate strings. Having said that, as I mentioned before, the things that you can represent with an NFA are exactly the same things that you can represent with a DFA, and vice versa. And there are standard algorithms that allow you to convert an NFA into a DFA. The algorithms, however, oftentimes mean that you start off with something relatively simple and you end up with many, many more states. Sometimes there's an exponential growth to the number of states when you're converting from an NFA to a DFA. We won't be talking about the specifics of those algorithms in this course, but if you study this idea in other courses, you may encounter this idea.